Okay. So we introduced just a moment in the first one that Big Bang Theory is about the universe expanding, and I said that it's the universe itself expanding, and then we talked about the evidence for that. And so the first bit of evidence is something called the Doppler Effect, which you may have heard of. We're going to look at that in a bit more detail now. Let's imagine the Doppler effect with respect to light waves, and you get the Doppler effect with all waves, including longitudinal and transverse. In essence, if something is producing a wave and moving away from you, the wave that you perceive is stretched. It has a longer wavelength than if the object wasn't moving. And the same would happen if you moved away from the object that's emitting the light. You would perceive a longer wavelength. And you can kind of imagine that because as the wave's coming towards you, the front of the wave is, well, I'll tell you what, we'll demonstrate it with this little star then. So the star's sitting still. It produces a ray of light which spreads around, or several rays of light. We can call this a wave front, and it stretches and it starts to spread out. It gets further and further away, like that. And of course, it's producing a wave every time period. Every period of time, which we call the time period, the amount of time it takes for one wave to be produced. So the first wave has got this far out. The first wave after another wavelength, after another time period, the first wave is now this far out, and the second wave has got to this point. And then after another time period, the first wave is now this far out, and the second wave's got here, and the third wave's now here, and so on. So if you draw waves against this, you can see that the waves, the sort of middle point of the wave, pretty much should appear at every point there on the circle. So if you sat watching this wave, whatever it might be, a water wave, a sound wave, a light wave, you would experience the same wavelength wherever you are. You can see the distance between each line is the same from whatever angle. Now, if the star is actually moving, once again, the first wavefront gets to that point. After the second wave, at the second time period, the first wave started from this point where the star was at the start, and the second wave has now originated from where the star is now. So this shows you how we originally think of waves as being stretched and squashed when we think about the Doppler effect, but it's not really true, is it? It's more that the object is moving. Well, okay, I know I said a moment ago that the objects aren't moving, but space-time itself is stretching, but the effect ends up being the same. And this effect repeats itself, and you can see that the faster the object would be moving, the greater this effect would be. So the more stretched the right hand ones would be, and the more squashed the left hand ones would be. So now, if you had somebody standing there, they would see a shorter wavelength, and somebody on the right hand side would see a longer wavelength, and that's the same with all waves. So just briefly then, with all this effect happens with all waves, and so on the left hand side you see a shorter wavelength, on the right hand side you would experience a longer wavelength depending on how you are perceiving that wave. We perceive light waves of different frequencies by perceiving different colors. We perceive sound waves as different frequencies by perceiving different pitches, and so this type of Doppler effect with light we don't really experience in everyday life, but we do experience it with sound waves. So I'll just demonstrate that now. Okay, so when I say demonstrate it, I'm going to show an animation. So we've got, but this points out something that you might be able to hear. So I'm going to share my computer sound actually, so you'll be able to hear it. But I don't think on the video it will actually. I don't think it will appear on the video. So I know what I'll do. I'm going to temporarily turn on my speakers so the microphone will pick up the sound. So let me just do that. Just pause it a second. Okay, so the speakers should pick it up now. So we're going to get this ambulance driving by this person, and we're going to do it at 34 meters per second, which is Mach 0.1. What that means is 0.1 the speed of sound, so a tenth of the speed of sound. And let's have a little listen. You can see at the moment she can hear the sound, and it's making a certain type of sound. I will just wait until it finally gets past her, and you'll notice that the pitch will drop as soon as it passes her. So that experiment in real life can be done out and about whenever a car drives by you, especially if it's got especially an ambulance or a police car drives by you. You'll notice as it comes towards you, it's got a high pitch, and as it goes away from you, it's got a lower pitch. And if you were in the car, you would hear a pitch somewhere in between those, because if you're traveling with the wave, then you're not going to experience any sort of Doppler effect. And if you had it at a faster speed, then it's going to be the Doppler effect is going to be greater. So we'll just have a listen to that. So now the pitch is even higher pitched as it's coming towards her. And it's even lower pitched as it's going away from her. So you get a Doppler effect with all waves, including sound and light. And just to show again how the Doppler effect works with light, if I move this galaxy towards somebody, you can see the waves at the front getting squashed up and the waves at the back getting stretched out. They've coloured them in blue because it would be it's more likely we're going to see blue if it was coming towards us. And if it was going away from it, it's more likely to see red. I mean, it's not strictly true. It basically means that the wavelengths would be stretched, and red has got a longer wavelength than blue, but it depends what colour it was at the beginning. So, in fact, it might not even be visible light at all. It might be stretched so much that it's no longer even visible. So we know that the light is a part of electromagnetic spectrum, and if it's more stretched than the longest wavelength we can detect, then it goes into the infrared, and after that it goes into microwave, and after that in radio waves, and vice versa. You can go into if you squashed it, it'd be eventually ultraviolet, and then X-rays, and then gamma rays. So basically they looked at distant galaxies. Not the case with some nearby galaxies, and certainly not the case of things within our own galaxy, that most things were moving away from us. Most things had a red shift, and so in its light, and so it was assumed that they're moving away from us. You do notice some redshift things, but they're not distant galaxies. They're usually, for example, you might see a binary star system rotating around, and as one of them is moving away from you, you'll see redshift, and as the other one's moving towards you, you'll see blue shift. So we do experience blue shift as well when we look out into this night sky, but most of it's the distant galaxies are redshifted. And more to the point, as I said in the first video, the ones that are moving away faster have a larger red shift. Okay.